So today we are looking at, we are continuing with partial differential equations, but we are going to go and look at the separation of variables where we will be applying the techniques for separation of variables on the wave equation. So we are looking at the wave equation. We are going to evaluate the wave equation using the principles of partial differential equations. So with this one, we say, let me just give a diagram, sort of like the concept behind. So we have a string that is displaced. So this is the x. We have a string that is being displaced. So the string is fixed between two ends, which is O, and L is fixed between two ends, and L represents the entire length of the string. So this string is just displaced. It's just displaced, and we are going to represent the y-axis as u is equals to f of x t. So what is going on here? So we have a string that is displaced between two fixed points, right? And we are saying we can choose a position P on the string, and that position P will depend on the distance from one end, and also will depend on the instantaneous time. So at this point, we can evaluate this point based on the distance from one end between these two ends, and also the time of displacement at that point. So if we are taking notes as our initial point, so the displacement here, or the displacement here to P is going to be x. So we are saying we are looking at the position of P on the string, which depends on the distance from one end and at an instant in time. Its displacement u represents the displacement. Its displacement u at any time can be expressed as u is equals to f of x t. This is the displacement of the string being displaced. It's just like when you're plugging a string. You pull it, you're pulling it at this end, you're pulling it, and then you let it to oscillate. Okay, so now we are saying there's an equation that governs the motion of this string. The equation is the wave equation, which we write as dx squared is equals to 1 over c squared d squared u over dt squared, where c is equals to, c is basically constant, but in our case here, c is a constant. But when you look at it's just the material constant determines the material that we're using. In our case, we're using a string, so the constant c will contain the mass per unit length of the string. It will contain the tension of the string, etc. So, but c is just a constant. So we are given this wave equation. So now we are tasked to find the general solution for this wave equation. So we need to simplify it and find the general solution. We are tasked to find the general solution. So what do we do here? First of all, we need to identify boundary conditions. We need to identify the boundary conditions. So just as we said, the string is fixed between 2 points, at this point, between these 2 points, we can see that the displacement is 0, right? And then also at this point, we can see that x is 0. At this point, we can see that x is L. So we are saying when u is equal to xt, right? So we are saying when the displacement is 0, when x is 0 at times t, this is this point, and then also the displacement is going to be 0 when x is L, also just going to be 0, which means we can just write this saying for all values of t, which is the time, for all values of t is greater or equals to 0. So for all values of time, when you're measuring the time while the string is oscillating between these two fixed values, looking at the initial point and the final point, you can see that from the initial point, the displacement is 0, u is 0 here, and also here u is 0. So we can say that at those points, at the point where x is 0, u is 0, at the point where the x is equals to L, the displacement is also 0 for all values of time. And then also we can say that at point, if the initial point of deflection P, if the initial point of deflection P at t, if the initial point of deflection P at t is equals to 0 is, let's say, denoted by f of x, then u x at time 0 is equals to f of x. So that's another condition. We are saying if this point P is deflected at t is equals to 0, then ux 0, because time is equals to 0, is going to be f of x. So that's another condition. So ux 0 is equals to f of x, point of deflection. And then this is the first, this is the second, and then you have the third. The third point here, we are saying the third initial condition. So the velocity, because remember, velocity is the rate of change of displacement. So the velocity of point P here, when it's being displaced at t is equals to 0, is denoted using g of x. So these are the three main boundary conditions that we're going to be using to simplify this wave equation. So now the first thing that we're going to do, we need to assume a trial solution. So we are assuming that there's a trial solution for this equation. There's a trial solution for this equation, which is ux t is equals to x t, so that we can be able to use the separation of variables. So from here, remember, this is our equation that we want to evaluate. So using the trial equation, we need to come up with the second derivative with respect to x, and also the second partial derivative with respect to t. So this is what you're going to do here. So let me just rewrite this in its simplest form. This is xt, like this. So now let's differentiate this with respect to x. So we are going to have du dx is going to be x prime t, and then if we differentiate this, du dt is going to be xt prime, and then d squared du over dx squared is equals to x double prime t, and then d squared du over dt squared is equals to x t double prime. So now from this trial solution, we have represented the second derivative, the second partial derivative with respect to x and with respect to t, and then we are going to substitute in our main equation. Remember, our main equation was d2u dx squared is equals to 1 over c squared, d2u dt squared. So now the second derivative with respect to x, sorry, is what is this? So we are going to have x double prime t is equals to 1 over c squared, and then with respect to time is x double prime. And then from here, what you do, you want to simplify this. So now you are going to keep all variables of x on one side and all variables of t on one side, making sure that the numerator contains the highest derivative. So here we are going to have x double prime over x is equals to 1 over c squared, right? Is equals to 1 over c squared, t double prime over t. And then this is what you do here. In order for you to able to separate these two terms, you need to equate this entire equation to mu. So what is mu? Mu is a constant. Mu is a constant. Mu is a constant. That mu is a constant. Why is it a constant? Because mu is independent of x and t. So mu is a constant because it's independent. It's independent of x and t, right? So we are saying we are equating this equation to a constant mu that is independent of x and t. That's why we are calling mu a constant. So now we can separate these two to x double prime over x is equals to mu, and 1 over c squared t double prime over t is equals to mu, right? So now let's rewrite this. We can rewrite this as x double prime minus mu x is equals to 0. And then also this side we can write this as, since we multiply, we are going to have c squared mu t, right? And then bring it this side. It's going to be the same thing as c squared mu t is equals to 0. So we have these two forms of equation now. So now we are applying the d operator. You have to remember how we solved second order homogeneous differential equations. If you want to find the auxiliary equation for a second order homogeneous equation, so we are going to do the same thing with these two equations. So I'm just going to go straight to the auxiliary equation. So this is going to be m squared minus mu is equals to 0. Same thing here. This is, instead of using m, let me just use another variable, lambda squared minus c squared mu is equals to 0. It's the same thing as m here. Let me just be consistent with m squared also. So here m is equals to plus or minus m is equals to plus or minus mu. M is equals to plus or minus root mu. And then also here m is equals to plus or minus c root mu. So this is what we have. We have two distinct values of m for both equation. So we can rewrite this, the solution for the x variable to be, so x, remember, if your auxiliary equation, these are auxiliary equations. If your auxiliary equations have, if the roots for your auxiliary equations have two distinct values, so you're going to represent your general solution or your cumulative function as a, as an exponential of, so the first one is going to be root mu x plus b e minus root mu x, right? And then for t, it's going to be the same thing. I used a, b here. Here I'm going to use c. A, b are constant. So c is also a constant to the power c root mu t plus d e to the power minus c root mu t. So now we have the cumulative function for x and t, so we can find the general function. Remember, we said the trial solution should be xt, so this is going to be a e root mu x plus b e minus root mu x times so this is going to be c root mu t plus d e minus c root t. So this is our general solution for the wave equation. So this is just our general solution, where you need to define every constant that you have, let me just write where a, b, c, and d are constants. These are just constants. So now, but then you can see that our general solution is with respect to mu which we declared earlier as a variable. We declared mu as a constant, sorry, not a variable. We declared mu as a constant right here. So then now let's look at the cases whereby we are going to evaluate mu at 3 different cases. So the first case we are evaluating saying that let mu to be greater than 0, because it's a constant, but we don't know where does it lie. So now let's start with saying case 1, mu is greater than 0, and to give mu sort of like a value, we're going to say let mu be equals to p squared. So we know that where p represents any value, any constant, and if you substitute p with any value, whether it's negative or positive, it's always going to be positive, which satisfies this statement. So from here, we are saying let mu to be equals to p squared. Let me just write this where p is a real constant. Where p is a real constant. So from here, what are we going to do? So where there's mu, we substitute, we replace with p. So let's rewrite our general equation to be a e to the power it's squared, right? So square root of mu is going to be p. So that is very important. So here we are going to have px plus b e, right, minus px, isn't it? And then here we are going to have c e. We're going to have c e minus, we have c cpt plus d e minus cpt here, right? So now we have where there's mu here in the main equation, we substituted with p squared. Okay, so now here, we are going to apply our boundary conditions that we stated earlier. So these were our boundary conditions. So we're going to start with these ones, with the first one. So we are given this. We want to see if mu is greater than 0, will the solution of the equation still hold? So if it doesn't hold, we look at another case. So from this one, we are applying the boundary conditions. So the first boundary condition we said new when x is 0 at time t, the displacement is going to be 0, which means this is the fixed point, so the first fixed point. So let's apply this. So this is going to be 0, so 0 is equals to a, x is 0, so e to the power 0 plus b e to the power 0, and then we're going to have c e cp t plus d e minus cpt, like this, right? So if we simplify this, we're saying this is 0 is equals to now a plus b, then you have c e cpt plus d e minus cpt, like this. So now what we can see here, we are saying this is equals to 0, but then you need to look at this expression really close. So this this one with this one, we can see that this expression cannot be 0 for all values of t. So this CE CPT, because remember evaluating with t, using t, so if we take t here and we substitute here, not all values of t will give you this expression to be 0. So this c plus de minus cpt, this cannot be 0 for all values of t, right? What does this mean? This means so this means that a plus b is equals to 0, which means that this is the term that is 0, such that if you multiply this term with this term, you get what? You get this 0. So that's the most important thing. So this means a and b is equals to 0. That means a is equals to minus b. So let's rewrite our original function. So if you rewrite our original function, you're going to get that okay, we're going to get that we have new xt is equals to, now it's going to be a outside, then you're going to have e, we're going to have e, remember we said new is p squared, so e px minus e minus px, right? Since here it was a, here it was b, so we substituted b with minus a, so that's why we have that. So this is multiplied by c e cpt plus d e cpt, right? So now from here we need to evaluate the second boundary condition. We are saying when x is equals to L, the displacement is 0. So even here, 0 is equals to, because the displacement is 0. So 0 is equals to a e p, now where x is equals to L, so pl minus e minus pl, so you have c e cpt plus d e cpt, like this. So now from here again, after applying the boundary condition, we need to evaluate which is 0, which cannot be 0. So remember, from the first boundary condition, we stated that this cannot be 0 for all values of t. So even here, this cannot be 0. This one cannot be 0 for all values of t. So we come back to these two. And also this is as a minus here, this is a plus here. So it oscillates. So this one cannot be 0 for all values of cannot be 0, right, for all values of x. So we are saying also EPL minus E minus PL cannot be 0, right? So now that means A is equals to 0. That means this is the A that is equals to 0. So that when you're multiplying everything else, you get 0. So from here, we are saying A is equals to 0. If so, now A and B are equals to 0. Because remember, we said A is equals to minus B. If A is B, that means if A is 0, that means B is also 0. So if A and B are also 0, then what does this mean? That this means, so this corresponds to the string being stationary. Why? Because if you come back to the original equation, if this is 0 and this is 0, which means everything, that means uxt is equals to 0, which is wrong, because that means that the string is stationary, but we know that the string has been displaced, right, 2 points P. So what does this mean? This case shows that this case suggests that we can say this case suggests that the string is stationary, right, which we know that is wrong. So this solution, we can just disregard this solution. This solution is disregarded. So this solution will be disregarded. Oh, this is the wrong spelling for disregarded. It's going to be disregarded. So let's try case 2. With case 2, we are still with case 2, and now we are saying let mu be equals to 0. Let mu be equals to 0, meaning with our equation, with our main equation, remember we had uxt is equals to ae. Now it's 0, so it's 0. Mu is 0. Where there's mu is 0 plus b e 0, and here we have c is 0 plus d is 0, right? So now from here, what are we getting? Okay, before we even come here, we can just look at this in this way. So let's take, for this one, let's take this. I think this is going to be the easiest way to evaluate this. So let's take this, the original equations that we got, these two. We're going to take these two. So we have x nu, x is equals to 0, and also we have t double prime minus c squared nu t is equals to 0. So now we are saying nu is equals to 0, which means x double prime is equals to 0 and t double prime is equals to 0. So that's what this implies. So when we are here, what then do we go about this one? So if you have a function that you differentiate twice, you get 0. What was the nature of that function? That means that function was linear, right? Because if you have y is equals to 2x plus 3, the first derivative of this one is going to be 2, and then the second derivative is going to be 0. So we are here now. We want to reverse from prime double prime to x. Even here, we want to reverse from t double t to t, right? So what do we going to do? Which means this, when you reverse, is going to be linear. So we can just say x is equals to ax plus b, and also t is equals to ax plus b. So now let's evaluate this one. So if x is ax plus b, we apply, or let me just use different constants here. So here is going to be k1x plus k2. So if again from here, from this case, we need to apply the initial condition. So let's apply the first one that says when x is 0 at any time there, the displacement is 0. So if we apply it here, that means 0 is equals to a0 plus b. This implies that b is equals to 0. Same thing here. And then if b is 0, then how are you finding a? So that means you have x now is equals to ax, isn't it? And then applying the second boundary condition where x is equals to L times t, and this one is 0, we are going to be left with what? With 0 is equals to a, where there's x we have L. Therefore, a is equals to 0. Also, a and b are 0, which means x double prime is 0 and x is 0. This is enough to tell us that, again, this case suggests that the string is stationary. Therefore, we disregard this case. We disregard this case, which means mu cannot be equals to 0. So let's look at the last one, whereby now we are saying case 3. Case 3, we are saying mu is less than 0. So what does this mean? We can also assign mu a value. The same mu is equals to minus p squared. So whatever value of p, because we're saying p is a real constant, whatever value of p, mu will always be negative, or will always be less than 0 because of this minus here. So now from this point, what do? Remember, initially we had x. Initially we had x double prime minus mu, x is equals to 0, and also a t double prime minus c squared mu, t is equals to 0. So now we are saying mu is equals to minus p squared. So where there is mu here, we substitute that. So this is x double prime plus p squared, x is equals to 0. Same thing here, t double prime plus, what do we have? We have c squared, c squared p squared, t is equals to 0. So from here, going to solve this equation, find our auxiliary equations, right? Find the root of the auxiliary equation. So from here we can see that m squared plus p squared is equals to 0. Also m squared plus c squared p squared is equals to 0. So from here m is equals to plus or minus I p, right? Because if m squared is equals to minus p squared, isn't it? And then root square root of a negative number, you get I, right? So that's how we evaluated this one. So this one is plus or minus I P. This one is equals to plus or minus I CP, right? So now, since we have your roots are exponential, we know that we can represent our final solutions here in this format. Remember that if your roots plus I beta, that means your final function is going to be E alpha A E beta x plus B E minus, this is plus or minus beta x, like this. So when after finding auxiliary equation, when you're finding the cumulative function of a second order differential equation that is homogeneous, so from here again you're going to have a, so from here you're going to have a cos px plus b sine px. The reason why we don't have e to the power, because this is 0 here, your alpha is 0, so e to the power 0 is just 1, so that's why we don't have it here. E to the power 0 is just 1. So even here we are going to have t is equals to c cos pct plus d sine pct, like this, right? So now here we can then write our equation as our general solution, as we wrote earlier, as px. So this is c cos pct plus d sine pct, like this. So now we have, after writing this, we can evaluate the boundary condition, starting with the first one, where x is 0 at times t. We know that the displacement is 0, so 0 is equals to, where there's x we have 0, so we're going to have a cos 0 plus b sine 0, and then this is equals to c cos pct plus d sine pct, right? So now sine 0 is 0, cos 0 is 1, so this is 0 is equals to a c cos pct plus d sine. So now the question is, what is a? So as we can see, again here you need to evaluate. We know that this term cannot be 0 for all values of t. So you write a statement that this term cannot be 0 for all values of t. Therefore, a is equals to 0. So if a is equals to 0, let's rewrite this one to show the simplified version. So x t is equals, if a is equals to 0, so we have b sine, so we have b sine px, right? And then we are left with c cos pct plus d sine pct, like this one. So now from here, what do? We evaluate the second. We evaluate the second boundary condition. If we evaluate the second boundary condition at yx is equals to L at t, the displacement is 0. So again here we are going to have 0 is equals to so from this one we have B sine, where there's x we substitute L, so C cos PCT plus D sine PCT. So now from here we need to determine which is 0 between these two. Obviously this one is not 0, cannot be 0. And from here B cannot also be 0, because if B is 0, which means automatically everything is 0, right? Even for the initial general equation, which is wrong. So now sine is equals to 0, sine PL is equals to 0 in this case, and PL is equals to sine inverse of 0, which is going to be n pi. Why is it n pi? Because if you draw your sine graph, which is continuous, right? You draw your sine graph, which is continuous. At every 0 point, we are going to have pi, right? 2 pi, 3 pi, it continues, and 3, 2, 1 represents integers. So n, that's why we are saying we have n integers times pi, because there are n solutions where n is greater or equals to 0, so all positive integers. So after knowing this, what can we then do? So we can rewrite this equation as sine n pi x over L. Then you have C cos Cn pi over L T plus D sine Cn pi over L T, like this. So what did we do in this equation where there is P, from here, cause from here I made P subject of the formula where it's n pi over L. So then where there is P here, where there is P in this equation, which is the symbol, yes, in this one where there is P, you substitute with n pi over L. So this is what you're going to get. So now when you're here, what do you do? Remember this, we have cause for this one we have a constant, we have a constant B here, right? Because set B cannot be equals to 0, and there's B here. So we have a constant B here. So now I'm going to take this constant B and multiply it inside here, such that we can say this is equals to sine n pi x over L a n cos Cn pi over Lt plus Bn sine Cn pi over Lt. So this one where An is equals to Bc and Bn is equals to Bd, because we're just multiplying the constants, right? And then now after rewriting your solution in this format, after rewriting this in this format, we can then say since we have n here, which means for any integer, when you evaluate this expression for any integer, we are going to get a solution, right, for this expression. So what does this mean? So we need to add all of the solutions. How do you add all of the solutions? Because n can go till infinity. So we can rewrite to you xt as the sum to infinity, from 0 to infinity of sine n pi x over L times a n cos c n pi over L plus bn sine cn pi over L t, or this is t, this is L, right? So, and then this is, when you look at this one, this looks familiar as what? This looks familiar as the Fourier series, right? So we've sort of like manipulated this one to get the Fourier series. But then now, what is our task? Our task is to find an and bn. Once we find an and bn, we are going to prove that the general solution for this wave equation, when nu is less than 0, does exist, right? So let's find an and bn. How do you evaluate an and bn? So the way we evaluate an and bn, we use the boundary conditions, but now we are going to use this one, u x 0, we said is going to be f of x, right? So that's going to be the function when t is equals to 0. And this we need to evaluate it from 0 to L. We're evaluating the value of x from 0 to L. Remember, when x was 0 and then we had t, we said t is greater or equals to 0. So we are doing the same thing here with x, just that with x, remember, we said when we drew the x-axis, we start from 0 to a point, a fixed point, the two fixed points, 0 and L. So x is in between these two fixed points. So now we use this equation, we evaluate this expression here. We evaluate x, we evaluate this one using this condition, boundary condition. So we are going to have f of x is equals to the summation when n is equals to 0 to infinity of, where there is t, we substitute 0. So this is sine n pi over Lx, and then we have where this t is 0, so this is an cos, this is going to be 0, right? So cos 0 plus bn, since there's t here, so we are going to have sine 0. So from here, sine 0 is 0, cos 0 is 1. So this f of x is going to be the summation when n is equals to 0 to infinity of sine n pi over Lx, right? And then this is multiplied by this an. So this is what we get for f of x, and then evaluating the other boundary condition, we are going to get that we said the other boundary condition says the velocity of the string at t is equals to 0 can be given as g of x, which means we need to differentiate this one. We need to differentiate this expression, this equation, with respect to t. So let's differentiate that with respect to d. Du dt is equals to, so we're differentiating this one, du dt is equals to the summation, is equals to the summation when n is equals to 0 to infinity of sine n pi over L x, since x we're differentiating with respect to t, so x is a constant. So now let's differentiate this an cos cn pi over L times t. We are going to get what? When you differentiate cos, we are going to get minus an, and then differentiate what is inside. It's going to be nc pi over L, right? And then remember, we are saying when t is equals to 0, because this is going to be sine nc pi over, because this is going to be sine nc pi over lt, right? But then we need to evaluate this t, because we know that t is what? It's 0. We said that t is 0. So if t is 0, this means it's going to be sine 0. And then differentiate this part. We are going to get what? If we differentiate that part, we're differentiating bn sine cn pi over lt. So we are going to get plus b, and then differentiate what is inside of sine, which is going to be nc pi over L, and then that is going to be cos 0, because we're evaluating at 0. So if it's sine 0, which means all of this is 0, right? So du dt, which is equals to g of x, is equals to cos 0 is 1. So this is equals to b nc pi over L. This is bn, sorry, this bn. Summation of n is equals to 0 to infinity sine n pi over L x. So this is what we have for G and B. So now we are going to using Fourier series. So using Fourier series, we are going to determine A and B. So using Fourier series, remember, an is what? Is 2 over L, and here we're using cos a is f of x, right? So a is associated with f of x, so this is going to be from 0 to L f of x sine n pi, right? Sine n pi x over L. This is dx, right? So this is the value of n if you use the Fourier sine series, isn't it? So again, to find bn, we know that bn is here, so we have n pi c over L bn. Using the Fourier series, we know that this is equal to 2L integral from 0 to of what? Remember, bn is g of x, associated with g of x, so g of x, then cos n pi x over L dx, and then here if you make bn the substitute of the formula, so your bn is going to be 2 over n pi c, the integral from 0 to L, g of x cos n pi x over L dx. So this was how you're supposed to solve this equation. So we started from we started from the wave equation. So we have evaluated the wave equation using the three cases, and after evaluating it using the three cases, we've determined that the last case, when nu is less than 0, is the one that is going to satisfy the entire equation. So this is how we have applied the principle of separation by variables to simplify and find a general solution for the wave equation. So this is how we are going to do it, and then from the next video I'm going to do an application of how to use these concepts when now we know when we have values on the boundary conditions. We are working with the values. We are no longer working with x, l, f of x, g of x. We are working with real functions and values. So this is it for this video.